Okay, so this is on the formation of stable margins to ice streams, or streams of fast-flowing ice in Antarctica. You'll see what I mean pretty soon. Early collaborators on that are Thibaut Perrault, John Platt, and Jenny Sukawi. The first two are now employed by this funny firm. I'm not getting any light here. So, was there light? No. Oh, there it is. Yeah, this funny firm called Stargram Labs. I have no idea what that means, but as you might suspect, they're a big data company, and that's what these guys do. Jenny was a postdoc who's now doing more or less conventional things like this sort of stuff at Stanford. And we have recent contributions from Colin Meyer, a recent graduate now at Oregon, and Alice Ariella, a postdoc, and Brent Minshew of Caltech, but now with the British Antarctic Survey. So here's what these stable margins are all about. If I can figure out how to go forward. Well, so much for that. Let's try from the keyboard. Yes. So here is a satellite-derived map of the Western Antarctic ice sheet. So that is Antarctica that you see there. And the square corresponds to this map. This is all covered with ice. The grayish areas are ice shelves, where the ice that makes contact with the Earth's surface below spreads out over the ocean. And this part within the box, Western Antarctica, is quite active. You have very rapidly flowing streams of ice that are identified here in different colors. So for example, what this map is showing are surface velocities as detected from successive satellite observations. The data is some 20 years old, and because what happened is when one satellite went out of operation, then another, there was no longer a complete data set. That has changed in recent years thanks to the Japanese and the Europeans who have put up satellites. So one could do this whole study today, but what the heck, 20 years, what's that in the age of the Earth? So we'll, and this data is there and available and easy to get. So what you see marked is the flow velocities. It's on a contour like this. And where you have blue, there's very slow velocities, 1 to 10 meters per year. And where you see these yellowish, orangish colors up to 1 kilometer a year, and indeed sometimes more. So what you see then are streams of ice, which is moving very fast up towards this kilometer a year range. And it's bordered by ice, which is marked in blue, which means it's barely moving at all. And these rapidly moving channels are called ice streams. And the question we want to address is, why do they exist, and what controls how fast they flow? Now, so there are the questions. I just asked them, I think. You might think, oh, they must sit in deep channels in the bed geometry, but that we know not to be true from just studies by seismic and radar reflections of what lies below. They sit on relatively featureless old seafloor, and indeed this area is thought to have been open ocean in the last glacial minimum. So they're in open ocean. They sit on a clay-like soil, and probably a good analog, if you know your soils, is London clay, another example of a marine deposit which is now raised above sea level. Yeah?
The velocity goes all the way down, or is it only the top? How deep is
The ice sheet ranges from 1 to 2 kilometers thick, sometimes thinner.
And the whole thing moves, or?
We believe the whole thing moves, but the observations only see the surface. So the interpretation is the whole thing is moving. But in any event, it's a clay-like soil, and we should remind ourselves of some things that civil engineers know very well. The strength of a granular material, a fluid-saturated granular material, is proportional, the shear strength is proportional to the difference between the normal stress, compressive normal stress, and pore pressure. So that concept will be important to what we get into in trying to figure out what processes might be important here. Okay, so that's another picture, and this shows you some places where data was taken in that great study of some years ago. So this shows traverses of the ice sheets. I wish I could make the pointer work. There we go. Traverses of the ice sheet where in general you have measurements on both sides of the stream. And there are 16 such traverses from satellite measurements, changes in position over time. Surface shear strain rates were measured. And what we have are averages over 2-kilometer widths near each margin. And this is what the data looks like. Never mind, let's leave it. This is what the data looks like in units of 10 to the minus 2 per year strain rate. And what you see is most of the strain rates are of the order of 10 in this unit. Sometimes more, sometimes less. There is one stream that's very slow. This is Cam ice stream, and it's a dying ice stream. We know that because when you go on that ice stream, I don't, when others go and write papers about it, what is measured is that there is fairly clear ice down to a certain depth, and I'm forgetting that depth, but of the order of 100 meters. So, and normally the margins of these streams is highly crevassed, full of fractures that form from shearing at the margins. So because this dying ice stream has no marginal crevasses until you go down past 100 meters or so in depth, we believe it's one that went inactive, and from current velocities we can guess a time over which it's been inactive. But this ice stream is going to play an important role because since its margins are not actively crevassing now, it is possible for people to go there and drill through. You don't dare send a team out in a crevassing margin. So that'll be important later. But you get the general idea of these things. And what we had the idea to do was, well, to ultimately use those measured strain rates to try to make rough estimates of temperature versus depth. But here's a schematic of a piece of the ice sheet. So thicknesses are in the order of 0.8 to 2 kilometers, at least in the areas that we study. Widths of these fast-moving streams are anywhere from 10 to 80 times the thickness. And you can easily work out a gravitational driving stress that has to be resisted somehow. It's just density times depth times slope, slope being of order 10 to the minus 3. And then you can look at what we know about certain stresses in this system. So we could say the lateral shear stress that resists this gravitational drive has to come, has to be resisted by, it resists the gravity drive plus a basal resistance. I just told you the gravity drive is of that order, 10 kPa. And from drilling through the ice sheet and measuring pore pressure and understanding overburden stress at the bottom and using properties of clays, as I mentioned, it was possible to infer that the basal shear stress is remarkably small compared to the driving shear stress that pushes these things along. And now if you think about a system like that, the wider a stream of moving ice gets to be, the bigger the lateral shear stresses have to be to hold it in place, right? Because you have gravity pulling on a wider zone. And that's kind of important. And we estimate these lateral shear stresses from simple equilibrium. This ignores variations in the general flow direction here, which have been carefully justified only in one case, and we optimistically assume that that applies more generally. But you see the lateral stress that you would need increases with width of the stream, and that of course causes a problem, because if you increase the width, well, you happen to be an ice whose strain rate goes roughly a stress cubed, so that gives you a width to the third power, but then that means your shear heating goes up with that power, so the shear heating rate goes as width to the fourth, and ultimately if these things tried to get arbitrarily wide, melting would have to set a limit to how wide they could be. Now, why is this up here? Yes, I think I somehow went backwards. Yes, so here's an idea we had, was to take that satellite data and try to use it to estimate what were the temperatures near the margins of these ice streams. How close would the ice in fact be to its melting point? And we've had several goes at this by increasingly sophisticated model, but this is a simple one-dimensional model where you say, well, it's a wide sheet to a rough approximation. Perhaps the velocities are not too non-uniform through the thickness. Let's act as if they're uniform throughout the depth of the sheet and make a simple one-dimensional model. So then the divergence of the heat flux, so K is thermal conductivity, T is temperature, that plus the rate at which you do work by deforming the material, the shear stress times the lateral strain rate, where we understand the shear stress is going to depend on strain rate and temperature. That has to balance a term that comes from advection, so W is the rate of vertical advection. There has to be a vertical advection because you're constantly having precipitation falling, yet the thickness of the ice over time doesn't seem to change very much. So there has to be such a term. And so we worked out, and it's the royal we, Thibaut Perot was mainly the guy who did that, solutions that were constrained by saying, well, the temperature must always be less than T melt. And we use those measured strain rates at the margins. And what we found, well, first, where did we get the data for this? And if you open sort of the Bible on glaciology, this is sort of the recommended flow law for generic glacial ice, so-called Glenn's law. Strain rate proportional to stress cube with a temperature-dependent factor, or stress proportional to the strain rate to the 1/3. And if those strain rates get too small, then you have to worry that other mechanisms could come in and contribute too, such as diffusion creep, but this is rarely important in what we look at, or so we think. And marked here is a very, very important fact about ice, which you may or may not know. But ice is unique among substances, or I think that's unique, in that it stays strong at its melting point. So if you want to deform ice, which is right at its melting point, you must do work on it. You must apply stresses. If you're doing work on it, thermodynamics says there's got to be an energy change somewhere, and the energy change, of course, is by producing melt. So the ice is, if you deform it, you are causing it to melt. And in fact, here at the melting point, you can see that for a given strain rate, the ice would be have about half of its strength at minus 13 Celsius. Now, why pick minus 13 Celsius? A typical range here is 0 to minus 26, so it's kind of in mid-range for the ice sheet. Minus 26, a good yearly average surface temperature, 0, a good yearly average basal temperature. And there's formulas for the conductivity. Here's what we found, and again, the royal we, Thibaut found this. Thibault-Perot. The temperature profiles, when you work them out, and Thibault did this with the constraint that the temperature could not get above the melting temperature, all of these, or almost all of these zones, have a substantial zone near the bed of the ice sheet, which is right at the melting point. Anywhere from 98 meters thick here to over 400 meters thick there. So it means that this simple model at least suggests that the margins of these ice streams are actively melting. They're being rapidly sheared and actively melted. Now, a slightly more refined version of that calculation led to something like this. So here is a plot of strain rate at the bottom in units of 1/year. And two things are plotted. So what we did was a one-dimensional analysis of this, assuming strain rate is uniform through depth. I know that can't be completely true, but it's probably okay for rough calculations, which we're doing at this point. And what you see here is, by calculation, as a function of strain rate for an ice sheet of some given thickness, what fraction of that sheet is temperate? That's what the dashed line shows. And then what is the thickness average shear stress supported by that sheet? And that's what the solid line shows. And you have this bump, this discontinuity, which actually makes this a triple valued stress versus strain rate relation. Is Roy Sayag here? Yes. So Roy speculated that such features might develop in ice sheets with other things in mind. I don't know whether you had this mechanism in mind or not. No. But it's what emerges from the calculations, triple valued. Now, what are these crosses? Well, the crosses are the data. In other words, you take the strain rate I measured and ask when you intersect these curves. And this is a single place at the margin, but it's a fairly generic picture, as I now show you for a bunch of margins. Most of them seem to be living at a place where we are well beyond that first peak in the curve. And that means that you have a substantial part of all of those thicknesses that are melting. Okay, now let's, with that background, let's focus on a particular ice stream and one margin of it, which has the name Dragon Margin. Glaciologists seem to like exotic names, and why that's called Dragon Margin, I don't know. But you see this little patch of blue and a patch of blue over here, and then a piece in the middle, which is moving really fast. I'll show you how fast, I think, on the next page. But it's not quite identical to this profile called WB2, but it's the place where we have the best data, we think, of anywhere near an ice stream margin, and that's why we focus on that. So here's a picture of that margin and a line along which there is data. Look at this speed, 420 meters a year. If you believe Hebrew University of Jerusalem puts out accurate maps, then I can tell you that this building in a year, if moving along at that rate, would be past the library, totally past the library. I obviously use the HUJ map to do my calculations, so it depends on how good those maps are. But it's going very, very fast. And then here, as you saw, this was colored in blue, so it's certainly less than 10 meters a year, and in fact, it seems more like 3 or 4. But that's the region we look at. And more details about the data are here. And by taking differences of measurements, we actually get a distribution of surface velocities and strain rates here. So this is that Dragon Margin that we're looking at. The ridge is sometimes called the Unicorn Ridge. Okay, so let's try to think of a shear margin. And where we're going here is our simple 1D models have suggested maybe we have substantial temperate zones, that is, zones deforming right at the melting point, near the margins of glaciers, is that supported by more sensible calculations? And that's what we've attempted to do here. So if you know crack mechanics, it's a configuration that we would call antiplane strain, but the flow is in the x direction, that's downstream, y is across stream, and z is vertical, and we're looking for a solution which varies just with vertical and cross-stream positions. So divergence of the antiplane shear stress vector has to be 0 or balanced by the part of the body force that acts downstream. And if you use Glenn's law to write equivalent shear stress in terms of strain rate and temperature, and then figure out what stress components are, this equation, this divergence type equation with a source term here, has to give 0. And sometimes we use slightly more complex views of the ice rheology where we say, well, in different stress ranges, there are different regimes that are valid. That's particularly important if you're in regimes of very low stress. The dislocation creep is appropriate for sort of higher stresses, and we think kind of typical stresses. But if you're really creeping at a slow rate, the main accommodation mechanism might be grain boundary diffusion. So one has to put things in the program to account for the fact that maybe you're in an anomalous region where one mechanism is so slow that the normally neglectable other one has to take over. And of course, they're thermally activated mechanisms. Anything else to, yeah, and of course to the equilibrium we add a thermal energy equation. And there are many ways to study this kind of system. In work of ages ago on crack mechanics, we spent a lot of time, the royal we, this is, looking at antiplane strain problems in crack mechanics because they were so easy to solve, and many nonlinear elastic plastic problems, if you like, were solved. So, and a lot of that methodology could be applied. In any event, in the end, we could do what we thought were more realistic calculations. And what did they show? Well, here is a portion of that ice stream near the margin I just showed you. And here are the thicknesses of the order of 1,000 meters. And this shows you a zone which in our calculation is concluded to be temperate, to be right at the melting point. It looks very thin, but you must realize there's a great exaggeration of vertical and horizontal scale. That zone is actually 2 kilometers wide at its base, whereas the whole ice sheet is about 1 kilometer high. So it's a massive zone of ice which is temperate and deforming, and hence it must be exuding liquid water. Now, we could do other models of this. For example, if you imagined an incredibly fast rate of motion of the cold margin into the stream, then the advective effects of that would totally wipe out any temperate region at all. We think this is an utterly unrealistic number for that, given that the downstream component of the motion of the ice on the ridge is less than that, and the ridge would have left a funny trail if it was actually moving laterally at that. But this just makes the point that one of the unknowns in this is how important really is horizontal advection into our ice stream, and this says if it's big enough, it's very important. You see that the model which has a temperate zone does a decent job compared to the data. These models do not. So for that reason, we tend to neglect this, but it is still a question mark in the work. Now, ice, and how does it deform? So,
These
yeah.
are the data taken from this CAM ice field that's not moving?
Sorry. No, I mean, this is that piece of ice that I showed you that was plowing along at 420 meters a year, and we are looking near its margin. So this is the part that's barely moving at all, and we are looking at the region.
The temperature data that you're using.
We calculate the temperature. We know the surface temperature, we know the base is temperate, so we know the water is right at the melting point there. And we calculate the temperatures through those equations I showed you. So they were coupled equations for temperature field and for strain and stress field. Okay. Yeah, now there's beautiful work by Charles Frank and Joseph Nye on how water moves through ice. And it was built on Frank's earlier contributions to the motion of melt in Earth's mantle. I think many people in physics don't realize that Frank had a second identity in earth science, but he made very substantial contributions there. And I'm not going to go through the details here, and I'm not going to discuss these equations at the bottom, but basically they're showing the water typically lives in grain boundary triple junctions, and ice is permeable because the water moves along channels along triple junctions, and the existence of those channels is thought to rely on the fact that the ice is impure. If you had really pure water, so it's claimed, no such channels would exist, but the small effect of impurities in the ice, and of course just through precipitation, raindrops coming down through the air, pick things up and so forth. So there are many ways that impurities get into the system. Okay, ignore the equations at the bottom. I just wanted you to see the pretty picture and understand how that allows the ice to be permeable. Now, look at this. Does that show well from where you are? There's a hole here. Can you see it? Oh, and it's beautiful there. So what that looks like is the municipal sewer company came out to this part of the ice sheet and laid a pipe in. But that's not true. Nature did that all by herself. So what happened here is that you're looking at the front of a glacier, which blocks at, now even this won't work. Oh, okay, it does, maybe. But it doesn't show on that screen. Okay, sorry about it. Yeah, okay. So, so if you go way back along this ice, up into the mountains where the glacier begins, you will find out that each year it dams a lake. What happens is springtime comes on, ice starts to melt, water runs down slopes, it piles up in back of a glacier, if the glacier is such as to block it. But as you know, ice cubes float in your glass of water. So once the depth of such a dammed up lake becomes as thick or more than 9/10 of thick as the ice sheet itself, the water underrides the ice sheet, and you get this massive blowout of water, which is a great way of making beautifully round tunnels sometimes, and other times not quite so round, but still tunnels. This is folks on an excursion from Juneau, Alaska, towards the Mendenhall Glacier in the U.S., and here are good scientific journal, the New York Times, reported on details of the outflows. And this next picture I show you just for its beauty, because while I would like to know more about it, I don't know a thing about it. But it's just so marvelous to see such a channel. And I'll point you to the very rough walls of the channel. That means any fluid that totally fills that channel and moves at any speed is obviously going to be in a turbulent flow with such effects. Okay, so we move along now to, so we're hypothesizing that, and because our calculations kind of require it, they generate water which has to go somewhere. We're hypothesizing that there is water in the margins of ice streams. As I told you, it's too dangerous to send people out to drill there, but we have this situation of Cam ice stream, which has roughly 100 meters of uncrevassed ice on top. So this was the target of a drilling program that was done by Barclay Cam in collaboration with some of his former students at one of the branches of University of California, Santa Cruz. And what they did was a set of drill holes where they tried, from looking at reflection data, to figure out where most complications were at depth. So they hoped that would be the shear margin. This should have been within the colder, slowly moving part of the ice, and I forget what the motivation was for that hole. But what they found as they drilled down is that they encountered first a layer of sediment-laden ice, 10 meters. If you have a vivid imagination, you would say, well, if there was a turbulent flow in a channel in contact with the bed, lots of stuff would have been kicked up and taken up in the ice above. But there was 1.6 meters of flowing water. And the fact that it was flowing was discovered because a camera was on the end of their drill string, and when particles would fall off into the water, they would rapidly get swept away. So we know that beneath this now extinct ice stream, there is now a channel, and so we, as I say, we have only one data point. This can't be done elsewhere, and it's very unfortunate. We have one data point, but the data point says our thinking is not yet to be thrown out as utterly crazy. So let's think a little bit about channels. Now, there's a beautiful theory of these channels. Basically, when you work it out, you inevitably conclude the Reynolds numbers are such that you're well into a turbulent range. So let's think about that. I've got a channel. It's conducting water, turbulent flow. So that means there's energy dissipation. So it means that that water is going to melt ice away from the wall. On the other hand, ice creeps. So the overburden stresses are constantly trying to close the channel. And Roethlisberger and Shreve simply worked out, separately by the way, the balance between the two, and said there's an equilibrium channel size when the rate of melting off the edge agrees with the rate of creep closure. And that's the kind of thing that's been calculated here. So this is done in terms of Manning coefficients, but may be easier to think about in terms of equivalent Nicarazzi roughness. And these are ranges going from a few millimeters up to nearly or about a meter. Now, we have some constraints that we can put on this, if I can find the right button to push. Let's try a button here. Yes, a man named Gary Clark, working in Canada, looked at a lot of massive flooding events under ice streams, typically by dammed marginal lakes, and tried to fit them with simple turbulent laws in terms of a roughness or Manning coefficient. And that's the range he found reasonable. And what we think might be reasonable for us is a more restricted version of that range, which should have popped. Yes. This simply seems big compared to the channel sizes we expect. And I forget whether it was pure bias or what made us think that these were too small. But in any event, we thought this as a plausible range. So Nicarazzi roughness is between roughly 2 and 20 centimeters. And for a given flow rate, you could then work out by this Roethlisberger-Shreve analysis what the channel diameter would be. And once you work that out, you could ultimately figure out at what pressure the channel is operating. And that's extremely important because whether the channel locks the ice to the bed depends on whether the pore pressure in the channel is a lot less than the overburden stress out here. And the answer we get is that it seems to be. If we want to calculate the shear strength of that place where the ice just meets the channel and meets the bed too, it would be the shear stress needed to deform it would be a friction coefficient of order 0.6 or so, times the difference between the hoop stress around that channel, the compressive hoop stress pushing the ice into the bed, and the pore pressure in the channel. And that works out to be, forgetting, I think, from the middle of a range here, about 150 kilopascals. Now, this is an extremely big number. You can look at the centers of ice streams where we have constraints on this sort of number too. And in the centers of ice streams, the basal resistance is less by a factor of 20 to 45 than what we're calculating at the channel. So in other words, the ice just on the sides of such a channel was much more firmly locked to the bed than is the stuff in the middle of the ice stream, which is good because that stuff in the middle was flowing fast. And these are very big factors. So we tried then to go back to doing calculations, this time using COMSOL, but the same basic geometry. We have an ice stream, we have ridges on the edge, we solve all the thermomechanical equations, but in addition, we now allow the possibility that water generated at the base of, we first allow the possibility there is a drainage channel, which is going to be a source of suction for any water and liquid water in the vicinity. And then there's a portion of the bed here, and we describe that, I hope, is described here. We simply, following some procedures of Cam and Engelbart some years ago of looking at water flows at the ice bed interface, we use a simple Poussey flow model, and we parameterize that by the thickness of a flow channel. We have no idea what to assume for such a thickness, but we just say, well, there ought to be some sort of hydraulic transmissivity of that channel that is the ice bed interface, and we parameterize it by the cube of a thickness, and we see what works. So this is the way we do it. This says the melt rate is the geothermal heat flux minus coming from below, minus what gets conducted out in the ice, plus the work rate of the basal shear stress on the velocity, all divided by the, what is L? It's the energy you put in per unit amount of melt. And that same quantity, the rate of generating water in the fault zone, in the interface zone, should be the divergence of this flux zone. So that's nice, we can all solve it. What we don't know are a lot of things here. So we have studied the way solutions depend on the thickness H of this Poussey channel, which just parameterizes the conductivity. Here's what we find. So this calculation has been done, and two versions of it are shown here, by putting a channel of a certain diameter, 1 meter diameter, in here, imagining it's flowing with water and it obeys all the equations of Roethlisberger channel theory. And then we have our gravity loading on this system from the slope of the ice. We know the surface temperature, minus 26 Celsius. The basal temperature, where there is moving liquid water, is fixed at the melting point there. And over here, where we think there may not be liquid water, the velocity is 0. The ice is just frozen to its bed. These are the cold ridge areas. So this shows you two different simulations, and the one free parameter that we just can't get a handle on directly is the thickness of this Poussey layer, an effective thickness, because it's really the hydraulic transmissivity of that interface that we're after. But this looks at nearly an order of magnitude range of values for that, and as you can see over that range, we are able to generate extremely good fits to the deformation data. So at least as far as being consistent with what is measured at the surface from deformation data, this works. So the picture we have now of the ice stream is you're looking at just a bit of it here. Remember, the channels are at the origin for both of these cases. This would be the cold ridge to the right of those of the origin, and then the center of the ice stream is here, and it extends all the way over to the other side of the stream. And what we are finding is that basically nature, if it follows the things we think it does, generates a Baron-Blatt self-resistive zone. So this is well known in crack theory. If you have a crack, and our interface between the ice and the bed is just a shear crack. If you have a crack and you want to, if you believe the crack has no singularity at its edges, you can achieve that if you have high resistive stresses to sliding near the bed. So what we have calculated as resistive stresses in the sorts of models I just showed you are plotted here. So this is meant to be where the channel is. This is the center of the ice stream. So the whole stream is twice as wide. And what we have is a low level of basal resistance consistent with the sort of measurements I mentioned at the beginning by Cam and his co-workers. But as you move away from the center and towards the margin, because of these greatly diminished fluid pore pressure and hence enhanced strength, you have a much, much higher stress needed to cause flow. So basically, this wipes out in the same way Barenblatt zones do in ordinary fracture mechanics. It wipes out what would otherwise be a singular point here and gives you a smooth solution to the problem. So that's basically all I have to say, except a few illustrations of how this looks. So this shows you some details of results of the calculation. So what's here is the basal yield strength, and that depends on what the local pore pressure is, what the overburden stress is, and of course the assumed friction coefficient. So this is the stress you have to achieve to get the interface between the ice and the bed to slide, plotted that way. And this is a distance in meters from the channel. And then what the solid lines are the basal shear stresses under different assumptions about what number we use, whose cube basically parameterizes the hydraulic conductivity of the interface. And you see you get cases where the stress equals the strength, which means the interface is sliding up to a certain point, and then the stress is less than the strength, and so the interface is locked. And where that transition between sliding and lock takes place depends on what we assume for the thickness of the Poussey layer. But that's generally what the solutions look like, and this is just a small technical point. Here's a case where, at least superficially, it looks like the predicted stress is bigger than the strength, so this solution must be no good. But having mentioned Barenblatt once, I can mention him twice, and we can stick in another Barenblatt zone at the end here and actually extend the range of this model out even to this extreme case. So over a very wide range of values of that hydraulic conductivity, that's what we have. We have a mechanism which basically makes the ice stream pay for its success in wanting to generate all that heat and all that water by having the water turn around and lock it in place. So that's what we think happens. I think I probably don't have time to go into this. How am I doing with time? 4 or 5 minutes. Okay, maybe I do have. So this is a more recent work which has been mainly done by Colin Meyer and Brent Manchu and my postdoc Alisar Yeya, with me being a cheerleader for them. But it looks at Bin-Schadler margin. Now, years ago in a paper that came out around, I don't know, maybe it was 1913 or so, Thibaut Perrault and I pointed out that we predicted part of this margin was frozen to the bed, but measurements from another part of the margin did not were not consistent with it being frozen to the bed. So what the gang listed on the previous slide did was try to use more sophisticated treatments of melting within the ice. So there's a group of Tristan Schuff at University of Vancouver and Ian Hewitt at Oxford University, who have put together ways of modeling melt generation within deforming ice, but doing the hydrology in a much more complete way than we've done here. And what those folks, my coworkers, did was apply that methodology to this Bin-Schadler margin, given the anomalous results I mentioned on whether it's temperate or not from simpler looks. And this is the first example, I believe, that exists in the literature of having a margin a channel begin from zero size and grow as it goes downstream. So that's sort of what's depicted here, the channel starting here and enlarging as it goes downstream. Of course, the longer it gets, the more cross sections are dumping water into it, and the wider it has to be. Let's see if any of these are more. This shows you the height of the temperate zone as you move downstream. So this is a total range of 50 kilometers downstream, but the temperate zone kicks in at a certain place and then grows, thickens as you go downstream. And this is looking at the porosity. I forgot to tell you, in the Schoof and Hewitt model, porosity is one of the variables that they solve for as you deform the temperate ice. And this is their prediction of porosity and how it varies. Porosity is important because what makes the ice porous and able to discharge the water is that it has porosity, and that lets the water seep down to the base or go over wherever, or into a channel or wherever it wants to go. And let's see what this is. Yes, and this is just emphasizing the importance of this effective pressure, which, as I said, every soil mechanician appreciates, normal stress minus pore pressure, and how it varies downstream. And the higher it gets, the more firmly you would tend to lock the margin in place. So those are little follow-ups to what I told you before. Conclusions: the transition from a slipping to a locked bed concentrates stress at the edge of an ice stream. Our model, at least without a whole lot more lateral advection than we can justify, predicts shear heating at the margins will lead to temperate ice. Hydrology, including Roethlisberger channel theory, suggests that such a channel reduces the stress concentration by locally strengthening the bed. Remember, it's normal stress minus pore pressure that determines the strength of the bed, allowing a smooth transition from a slipping to a locked bed at the margin. And that's quite analogous to Barenblatt, Dugdale, Bilby, Cottrell, Swindon-like crack models in fracture mechanics. Other mechanisms can increase locally the bed strength and allow stable margin configurations like freezing of the bed, or what some people like to call sticky spots, but it's not clear what they are. And the mechanism requires a channelized drainage resulting from a well-developed temperate ice zone somewhere along the margin. And this is more likely to occur downstream, that is, as you get towards where the ice sheet discharges itself over the ocean, than upstream where it was in its early stages. Okay, so I think that's all I have to say. Jay, happy birthday, and I want you to stick some ice into your apparatus in the future, if you don't mind. You know, pick a hot day when you'd like to have a little bit of cooling in the lab. Thanks. Yeah.
So there are some big ice shelves where the press has raised worries about them sliding into sea with unfortunate consequences for coastal civilization.
Some of them have recently slid
Right.
into the sea.
So what are this seems to have implications for that, but I'm not sure what they are.
Well, that gets to a problem, a part of the problem that I find too rough for me at present. I wish I had a handle on that. You might ask Roy Sayag. Where's Roy? He was here. Yeah, you might ask Roy. He knows a lot about that. I just don't have a good understanding of that transition range where the ice goes out and floats over the water. It's very important. Now, as you know from the newspapers, a vast area like that broke off from the rest of the ice sheet. Is that going to raise sea level?
No, because it was already in the water.
Exactly. Yeah. So the ice that
But if you had a big enough river,
Right.
the sort that you're talking about, if there was some instability where the width could diverge, then this could be a model for this integration of an ice sheet.
Yeah.
But you don't seem to be finding that. You have stable margins.
Yes, that's true, but then we're only looking over the time scale of a few decades here. And
That's fine. That's good enough for us in this room.
okay. Yes, you heard it.
Does this Barnblatt processor that is generated should vary laterally across the
The conditions within it do. The pore pressure within it, and hence normal stress minus pore pressure varies laterally.
lateral.
Yes,
So
that's
does
right.
this should maybe leave some signature in the rock after.
Well, yes, but you're only going to see the signature after several centuries. If we have a complete deglaciation, then if anyone's living on Earth, then they can go.
Okay, so in the last decade or 20 years, there are many glaciers, many places that were glaciers.
Yeah, but if you look over recent years, there's much less drilling into glaciers, and drilling is about the only way to get any good access. Some things you can do by radar imaging and reflection seismology, but to get details, you have to drill. And there's a big inhibition against drilling for biological reasons, that we will contaminate ecosystems that live down there.
But all of the recent glacier disappearance that has been occurring leave some exposed area that was covered by glacier.
But it keeps snowing. It keeps snowing, so you continuously have accumulation.
I mean, between land and I know some places in Alaska, near on land, it started on land, for example, but sort of going to the ocean, that 20 years ago there were glaciers and now there's nothing.
Yeah.
It's just rock exposed with potential signatures.
Right, and I certainly agree there's that long-term trend that we will have, rising sea level or sea level retreat. We're going to have change from moving all of this ice off the ice sheets in a short time. But I don't know how to make what I'm doing now make any contribution to that. We're simply trying to understand what could be the mechanics that allows the streaming nature of the ice at this point. Yes?
You made an assumption that in the margins there is some kind of a continuous creep based on these annual observations.
Well, it's hardly an assumption because we get significant strain rates.
Yeah, that's true.
Okay, yeah.
There is more, let's say there is shear along.
Yes,
Now, people talking more recently about ice quakes, including
Yes.
partly the responsibility of Jay.
yes.
He is also participated in this endeavor. So the question is, if the motion is not steady shear with the steady strain rate that you described, but rather ice quake in which portion of it moving and then freezing or healing, if you will,
Yeah.
if you use the terminology of Chris, then how would it change your calculations?
Yes,
So,
well, totally, because it's not in our calculations now, and if there were ice quakes at those margins, then you would think that would make a big increase, at least for some time before things refroze, a big increase in transmissivity of fluid downstream in the margins. Jay?
I actually had a related question, whether you think the ice quakes are due to basal friction or to just the margins breaking and reforming, because both could give you the same effect.
Yeah, the answer is I simply don't know. Chris has looked more at that. Where's Chris?
I'm here,
Yeah, yeah.
So it turns out that when you add some debris to ice, you can make it quite weak. That it could have an effect at the bottom. I don't know if it would do much for you at the edge.
Because to get a quake, you have to break the edges as well at some stage. So
Yeah, maybe. You don't need to move the whole thing at once, right? You can have a confined, you can have an area fluctuation.
Yes?
I have just a curiosity because you gave sizes at the very beginning. Can you give something like 1 kilometer, 2 kilometers, and then roughly between 100 to 200 kilometers? Because you said that was 80 times the 8, no? The white.
Well, let's...
Roughly
Yeah.
speaking, is that, okay, so you have a ratio, an aspect ratio between 1 kilometer, let's say 100 kilometers on the result.
Well, in the downstream direction,
In the
well
south,
more
yeah,
than
yeah.
100 kilometers,
But,
yeah.
So, I was just thinking, you have a stronger shear on the sides, and then this big mass that is formed. And, there should be a an incredible deformation between the center and the size.
But I believe that's what the strain rates measure. That's why the strain rates are up there about 10 to the minus 2 per year for the sides, and they're negligible in the center. So I think the strain rates are supporting exactly the picture you proposed, that there's a lot of deformation going on near those margins. Yes, you're right. Well, we have a measured width for the particular one we've really focused heavily on, and that's of the order of 30-some kilometers wide.
So how would the characteristics of the margin change if you modify it?
The way to get at that is to rephrase the question, how would the shear stress that the margin has to be support modify that? Now, we have looked at this great catalog of margins, as I showed near the beginning, and worked out from measured strain rates what we think the shear stresses are at those margins. So, I mean, if you want to know the shear stress at the margin, we have a way of estimating that, presuming that we have measurements of the surface deformation and presuming our assumption is not so bad that that prevails through depth. Does that get at what you're after, though?
It also
A little louder.
affect the melting rate.
Sorry?
It will also affect the melting rate.
Right, but our melting rate calculation is based on the measured current strain rates, or at least strain rates 20 years ago in the data set we use. So, yes, the bigger the strain rates are for a given ice thickness, the bigger the temperate zone is going to be. That shows up very clearly in the results, as it must. Okay. Sorry, let me get out of here. What happened to my computer? Oh, thanks. Sorry. Oh, yes, I'm sorry.
Continuous transition to the next session, which I'll be chairing. So it's basically, the title is the Next Generation in Feinberg's Lab, which means